today we're going to be talking about the concept of work. And work is something that you've probably seen before. Maybe it's come up in your past physics classes, or maybe it was even briefly mentioned in your statics class. But work is this idea of a force causing a movement over a distance, right? So a force does work when a particle undergoes displacement. That's like our technical definition of work. So we'll put that here. So a force does work when a particle undergoes a displacement. And then this is the important part. In the direction of the force. So this displacement in the direction of the force, that's really our really important part of work here when we're talking about work. Right, so it's this representation of displacement in relation to force that we use as a value to work with work and energy. So we're going to talk about work in this video, and then in our next one we're going to talk about work and energy and how those play together and how we can use those with our equations of motion, the F equals ma, and our position, velocity, acceleration, time. All of those things come together to basically unlock more ways for us to solve problems. So work, as we've said, and you may have seen it in your other classes, work is going to be force times the displacement. So you might have seen it in some classes. Some classes use W for work. We typically use W for weight in this class, so in order to not get them confused, in our class we're going to use the letter U, just the capital U for work, to help us not confuse it with weight and not confuse it with other things. So capital U is going to be the force times the distance. And really, in our vector formation, and if we think about this as as something that can change, right? Work can change over a changing displacement. We can have our changing work is going to be the vector F dot product with dr. So what we mean by that is if we have some, say maybe something like this, we have some fixed point. And from there we have r. We have r coming out from there. And then that particle moves from this location on the path to maybe this location on the path. They have another, call it r prime. Or what we have is this shortcut from r to r prime, that's our dr. That length of the path that they traveled along here is our ds, and that force that's acting on that particle that made it move in that direction, again, in the direction of travel, whatever that force is, that component that moves in the r direction, or in the s direction, the direction of movement there, that's going to be our force. So this relationship we can see as a dot product, or you can see it as the force times displacement. You might also sometimes see it as this, not in this dr relationship, but instead du is f cosine theta ds, for this angle here between our r initial and our final r position, that's going to be our theta. So f cosine theta ds, converting between whether we're looking at r or whether we're looking at s, r being that vector form, s being that displacement itself. So again, there are many relationships, many equations that we can derive with this u is force times displacement, where we play with these relationships of how the force is actually acting for the displacement in that direction of the force. So let's kind of go a little bit deeper into what does that mean? What is doing work? What are some examples of forces that do work? So if we look at, just have a box here. If I have a box and it's just sitting here, it has a normal force and a weight, and it's just, draw some table here, and it's just sitting there. There's no acceleration, there's no movement, it's just a box sitting on a table. In this case, the weight of the box is doing no work. There's no displacement, the box is not moving anywhere, so the weight does no work. Weight does no work, or we can say U equals 0 for the weight. Likewise, our normal force isn't doing any work. There is no displacement in the normal direction. And this is extremely common. We almost never see a normal force doing work because a normal force is just a response to a surface, right? So anytime you set anything down, even if you slam something down on the table, the normal force is not pushing it back up, unless you're on something like a trampoline where you have springs. That's an outlier case. A normal force will pretty much never do work. A normal force isn't doing any work. There is no displacement in the direction. So what if we put a force on it? What if it starts to move to the right? Okay, let's say I've got a box on the table. It still has the weight, the normal force acting on it, but let's say, okay, now I've got, let's just say a 200 Newton force, for example, and my box moves from its initial position here to here, some amount of time. Call this delta S, this is the displacement from that 200 Newton force. Then in this case, the weight and N are still doing no work. Like there is no displacement, there's no movement in this Y direction, but there is in the X direction. So we would have our U, let me not color. Our work is only of that 200 Newton force. So actually, let me do it this way. So the 200 Newton force does work. Does do work. And that work is going to be the force, so in this case, the 200 Newton force, times the displacement, delta S, however far it traveled. So that's our F times delta S. And notice that the displacement and the 200 Newton force, they're both in the same direction there, right? So both in the same direction, so it's the force causing a displacement in the same direction, just F times delta S. 200 times delta S. But what if it's not perfect, right? What if it's not perfectly horizontal? What if that 200 Newton force is making some kind of angle with the box? Here's our box sitting on a table. Again, still, it's going to move to the right, still. But now that 200 Newton force is acting at an angle of theta. 200 Newton force is acting at an angle of theta, and it's still being displaced by some displacement delta S, moving in some however many meters or feet to the right because of that 200 Newton force. So here the 200 Newton force still does work, but it's not entirely the full 200 Newton. Or now what we have, if we were to calculate it, we would only want the component of that 200 Newton force that's in the same direction as displacement. So I only want this X component of my force here. And so that's going to be 200 times cosine theta. Right? Only the X component of that force because that is in the direction of the displacement. Times delta S. Right, so here in this case, instead of having F delta S, we had F cosine theta delta S. And we'll have a lot of different work scenarios. Sometimes our force will be changing. Sometimes we might have spring force, have weight doing work, variable forces, a few different scenarios that we'll talk through in just a second, where we really have to analyze, is this force in the direction of displacement? Because that's how we're going to calculate our work. Before we look at those, I just want to make one quick note on these units for work. Our unit for work is going to be, since we have a force times a displacement, you will sometimes see it as just that force times displacement. So newtons times meters, Newton meters in our SI units. Now this is also a special SI unit in and of itself called a joule. So capital J, the shorthand, but this is a joule. And if we're working in US units, it's going to be in foot-pounds. Foot-pounds, foot multiplied by pounds. And we will note this is a scalar. So this does not actually have a direction associated with it. It is not a vector itself. Since it is a dot product gives a scalar answer. And work is a scalar. Don't have to worry about direction. We've really already built it in through the vectors, through the dot product. Let's take a look at a couple of special instances of work, some special formulas that may help us besides just these main overarching generalized work equations here. We'll look at just a couple of special scenarios before we look at an example. Let's talk about a couple of these special cases that you're likely to run across. And the first one I'm going to mention is actually one that we just saw with some of those little examples of how work works. So, for example, if we had in that first case some box that has that normal force and the weight and a constant force acting on it. So this is what we had just had in that last example, and it gets displaced from S1 to S2. In this case, in the case where we have a constant force not changing along a straight line, we can use a shorthand equation where we have the work from 1 to 2, so the work to move the block from location 1 to location 2, is going to be the force times cosine theta times S2 minus S1, right? So the difference in your position here. Really, delta S is what we called it in the last one, just that difference in. So this special case, again, this is if you have a constant force acting in a straight line. So it can save you from having to work with that differential form, that du, dr, ds, that form. You can skip straight to using just this simplified relation. Now another one that we might see is a variable force. Right? You could have some box on the table and it has the normal and the weight and all of that, but let's say it has, instead of that 200 newtons, now the force acting on it is 30 times S. So like the more it displaces, the more the force becomes. It's in direct relationship to that displacement from S1 to S2. So if we have this one where we have a variable force, we're going to want to use the integration, right? So we can use the integration. We're going to have the work from 1 to 2, work that takes a force to move it from 1 to 2, going to be the integral from S1 to S2 of that force, whatever that force function is. In this case, it's 30S. 30S times cosine theta ds. Right, so this is kind of a a more simplified, already built-in integral form, especially useful if your variable force is in terms of s. You may have to do some work to get it into that form, but we can do that and then use this integration. Another form of work we might have is from the weight of an object. So, for example, in projectile motion, you have the weight is doing work to bring that displacement back down to Earth. Throw something up. We're working in the y direction now instead of the x, where weight may be doing work. Weight is that force, pulling it down, causing a displacement. So you have some object, not necessarily on the table, maybe it's in space. The weight is doing work and causing it to move down by some delta y. So this work, the work of weight, may also be something that we want to consider. And we can use a shorthand formula for this one as well, where the work to move it from one location to another is going to be negative w times delta y. Negative since our weight is always pulling us down to Earth, right? It's a standard negative in our positive xy coordinate system. Since the weight is down, and we've got a negative for our work. And then finally, our last special case that may come up is going to be a spring force. Right, so if we have some force acting on a spring, S, ds, have that force of the particle pushing in on the spring. Our work of a spring is going to be, and you might remember this spring formula from back in physics, you might not. Work to move it from 1 to 2 is going to be negative for springs, 1/2 ks2 squared minus 1/2 ks1 squared. That's your final position, your initial position. S2 is final position, S1 is your initial position. And this is all negative work for a spring force. So these are like the standard, I would say, standard special cases, good ones to know, to have in your back pocket for when you're solving these work problems, because these will get you through pretty much any work scenarios that you're trying to figure out the work that a force is doing, so that we can then go relate these back to force, mass, acceleration, position, velocity, all of those things that we've talked about so far. Before we get to those, we'll just do one quick example to kind of see how work works. In this example, we've got a 10 kilogram block shown that rests on a smooth incline. If the spring is originally stretched by 1/2 meter, determine the total work done by all of the forces acting on the block when a horizontal force P equals 400 newtons pushes the block up the plane by S equals 2 meters. Right, so really, all it's asking us is to find the total work. And finding the total work is just going to be a matter of summing all of the work that is being done in order to push this block up the incline by 2 meters. So the first thing that we're going to want to do is analyze what forces we can have here that are working on sliding this block up the plane. So of course, we'll do that with our best friend, a free body diagram. And in our free body diagram, we have, of course, the body. Here's our little block. He is on an incline at an angle of 30 degrees. And then we're going to put all of our forces on him. So it says we have a 10 kilogram block, so we know he has a weight. Got that weight acting straight down. It's 10 kilograms, so 10 times 81. Going to give me 98.1 newtons of weight. Of course, we're also going to have the normal force acting on the block perpendicular to that incline, the normal force. It also tells us we have that applied force of P acting horizontally to the left on the block of 400 newtons. And then the last one, and maybe the trickiest one, is that spring force. So because it's connected to that spring there will be a spring force. It's in the direction of the plane. Force from that spring, it even gives us our spring constant there, 30 newtons per meter. So that kind of hints to us we've got to include the spring force included in our work calculation. So remember, our work is just going to be the force times the displacement. Just remembering that it is in the direction of the displacement. Okay, so when we calculate these for each of these forces, we'll go one by one through each force individually, see what work every single force is doing, and then just summing them all up to find that total. So I'm going to start with the thing I see first on here, which is the weight. So my weight, the work done by weight, as we discussed, is going to be negative W times delta Y. So this is work done by weight. Negative W times delta Y. So in this, we're going to have our weight is 98.1 newtons times delta Y. Now remember, this delta Y, it's in the direction of displacement, but it is our Y component here. Right? It's the Y component of our direction. So even though it's moving s equals 2 meters up along the ramp, the Y component of that direction, in line with that force, is 2 times sine 30. 2 sine 30. Be the Y component. So in the direction of movement, since we are moving up along the incline, up along that 30-degree incline, you can think about it as the Y component of the force. You can also think about it, if it's a little bit easier for you, to keep in mind that we're moving this way. This is our direction of S. We can make this angle here between our W and the where the normal force would be if we kind of rotated our axis so that now we're in the direction of movement. One axis is in the direction of movement, the other axis is essentially in the normal direction. We would have this 30-degree angle for the weight. So if we were looking at the direction that the weight is actually pushing, like giving towards displacement, it would really be this component of the force, right? Like, of this 30-degree angle, it's going to be sine 30, W sine 30. This purple doesn't good as I want it to. Right, so it would be like this component of the triangle. This is parallel to this S direction. You can think of it like 98.1 times sine 30 times the distance S of 2. Or you can think about it like the Y component here of the distance traveled, 2 sine 30 times the overall weight. Either way, whichever way your brain likes to think about it, it works out the exact same. It's still 2 times 98.1 times sine 30. All of those come together to give us the work of weight is going to be negative 98.1 joules. Right? Because 2 sine 30 is just 2 times 1/2. You just end up with the negative 98.1 joules. And again, negative because that weight is trying to push the block down the incline when the displacement in reality is going up the incline. So I'm going to keep coming down. The next one I see is that 400 Newton force. That 400 Newton force. So I'm going to say the work done by the applied force, I'll just call it P. Applied force P, that 400 Newton force, is just going to be, it's a constant force, it's just going to be our F cosine theta times S. The straightforward, or I guess delta S, F cosine delta S relationship. Where we're going to have 400 times cosine, then the angle we're going up, so cosine 30. Right, that's the angle that we're making, this angle here. 30, angle we're making with the S axis, you can think about it in the direction of displacement. And then we know the displacement is 2 meters. Whoops. 2 meters. We'll put that in for S. And that gives us a work from the E force, from that applied 400 Newton force, is 692.8 joules. Right, so that's positive, it's moving in the direction of displacement. Have that work of that applied 400 Newton. Now let's look at Fs. Let's go ahead and look at our spring force. So what is the work done by that spring? We had an equation for work done by a spring. It was negative 1/2 ks2 squared minus 1/2 ks1 squared. So we know our k, it's given to us in the diagram here, of 30 newtons per meter. Negative 1/2 times 30. And then what is our S2? What is our final S? Bear in mind that the original question told us that the spring is originally stretched 0.5 meters. So not only is S moving that additional 2 meters, but we have to keep in mind that the original S, S1, is 0.5, which means S2 isn't actually 2, it's the 2 plus the 0.5 that it was already stretched. So in total, at S2, this thing has been stretched 2.5 meters. So that's the S2 that we have to put in. We can't just put in 2. Going to be 2.5 squared minus 1/2 times k, again, is 30. And then S1, as we just said, that original S position for the spring was 0.5. 0.5 squared. And when we plug that into a calculator, we're going to get our spring, our work from our spring is, I can't find, negative 90 joules. Okay, and then just one more force left on our free body diagram, and that's our normal force. And if we remember, or think of this in terms of what our work is, our work is the force in the direction of displacement. The normal force does no work. It has no applied force in the direction of displacement. It's totally perpendicular to the displacement. So the normal force does no work. Normal force does no work. So we could put it in here. Normal force is 0. Absolutely no work. And with that, we've solved all of these components of work, right? The way each and every single force contributes to the displacement of 2 meters. So what we can do is just sum them all together to get what that total work is. So the sum of my works is going to be the normal work plus the work from the weight plus the work from E plus the work from the spring. So that's 0 minus 98.1 plus 692.8 minus 90 gives me a total work. Total work U is 505 joules. I get when I plug that into my total work, 505 joules, work done by all of the forces acting on that block. So now that we've kind of worked through what work is, how do we find work, that relationship between force and displacement, we're going to use this in the next video in working with energy to kind of explore more methods and more relationships to find your relationships between force, acceleration, velocity, position, mass, all of these inclusive, using these ideas of work and